Welcome to the deep dive. Ready to get quantum? Today we're diving into the world of quantum mechanics.
Yeah, a world where things get a little strange, a little mind-bending. But don't worry, we'll break it down.
We'll guide you through it all. No PhD required, promise. From the very beginning of quantum mechanics to, well, how it's actually shaping technology today.
Exactly. We'll be your quantum tour guides.
So, before we get too deep into the quantum realm, let's rewind a bit. Back to, the familiar world of classical physics.
Right, the physics we encounter every day. Think like Newton's laws, gravity.
The stuff that seems pretty straightforward,
Or
right?
real.
But as scientists delved deeper into like the microscopic world,
Yeah,
they started finding things that classical physics just couldn't explain.
exactly. It's like imagine you have this perfect model of the universe, and then you zoom in and it's all pixelated. That's kind of what happened.
Uh-huh. Yeah, the universe throws us a curveball.
And one of those big curveballs was this thing called the ultraviolet catastrophe.
Ooh, that's dramatic.
It was. Basically, classical physics predicted that a hot object, like really hot, should emit an infinite amount of energy as ultraviolet light.
Okay, that doesn't sound right.
Right. It obviously wasn't happening. That's where Max Planck steps in, a German physicist, as highlighted by Jorgo Schneeppert in their essay, Planck's Quantum Leap.
Oh, Planck, the quantum revolutionary.
Kind of, though, funnily enough, even Planck wasn't totally on board with his own idea at first.
What was his idea?
Well, he said that energy isn't this smooth, continuous thing. It comes in these tiny, indivisible packets, like little bundles.
Okay, I think I'm with you. So it's like saying, instead of money being this fluid thing you can divide infinitely, you
Yeah.
only have coins.
Yeah, exactly. Like you can have one coin, two coins, three coins, but not half a coin.
Right.
That's how energy works, according to Planck. These little bundles of energy, we call them quanta.
Quanta, I like it. It's got a ring to it.
Haha, yeah. And this totally wild idea. It actually fixed the ultraviolet catastrophe problem. It perfectly explained how light energy really behaved.
Okay, so Planck's onto something. But wait, was this just some math trick or were these quanta like a real thing?
Well, Einstein stepped in to answer that question and like solidify this whole concept of quanta.
Einstein, okay, now we're talking. What did he do?
He looked at something called the photoelectric effect. It's basically how shining light on metal can knock electrons loose.
Okay, so light can knock stuff around.
It can. Now, classical physics said the brighter the light, the more energy those electrons should have when they're knocked loose.
Makes sense, right? Brighter light, more energy.
Right, but that's not what experiments showed. Einstein realized it wasn't about the brightness, it was about the frequency of the light wave, like how fast it was wiggling. And he proposed that light itself is made up of these tiny packets of energy.
Oh, okay, so light is also made of quanta.
Yes. Those little light quanta, we call them photons now.
Photons, got it. So, wait, hold on. Are you saying that light acts like both a wave and a particle?
Yep. Welcome to the quantum world.
Whoa, how is that even possible?
It's one of the mind-blowing things about quantum mechanics. Things don't always fit into neat boxes like wave or particle. Sometimes they're both.
Okay, my brain is officially bending. Is there, like, any way to really picture this wave-particle duality thing?
Yeah, actually there is. Think about the famous double-slit experiment. It's a classic. Imagine shining a beam of light through two tiny slits onto a screen behind it.
Okay, I'm visualizing it. If light was just a wave, wouldn't we see a bright band behind each slit on the screen?
You would. But here's the thing. You'd also see an interference pattern, like where the waves from the two slits overlap and create these bright and dark bands.
Mm-hmm.
And that's what happens, even if you shoot single photons one at a time.
Right. So it's like each photon is going through both slits at the same time.
Yeah, it's like it's interfering with itself, like it's in two places at once.
Whoa. It really is like the universe is playing tricks on us.
It gets even wilder. If you try to measure which slit each photon goes through, the interference pattern vanishes. Poof.
Wait, seriously. So just by watching, by measuring, we change how they behave.
That's the quantum world for you. Observing something can actually change the outcome. And that's actually related to Heisenberg's uncertainty principle.
Right, Heisenberg. That's the idea that you can't know both the position and the momentum of a particle with perfect accuracy.
Exactly. And as Jorgo Schneeppert points out, it's not just that our instruments are limited, it's baked into the fabric of reality itself.
Whoa. Okay. So we've got particles acting like waves, waves acting like particles. The act of observing changing things.
Yeah, it's a lot to take in, I know.
My head is spinning. So how did physicists even begin to like wrap their minds around all this quantum chaos? Did they just throw their hands up?
Well, not quite. They came up with different ways of trying to make sense of it. Heisenberg, with his matrix mechanics, he went super abstract, focused on what we can actually measure.
Okay, so like a practical approach.
Kinda. Then there's Schrödinger, with his wave mechanics. He pictured particles as waves, using what we call the wave function.
Okay, waves. Got it. But wait, what does this wave function actually tell us?
Well, that's where Max Born comes in. He's the one who figured out how to interpret it. And it was revolutionary. He said, in the quantum world, we can't know everything with absolute certainty. We can only know the probability of finding a particle somewhere, or in a certain state.
Probabilities. So instead of knowing exactly where a particle is going to be, we just know the chances.
Exactly. That's a huge shift from a universe where everything is, like, predetermined to one where chance, randomness plays a role.
Okay, so it's not about knowing for sure. It's about knowing the odds.
Precisely. And this idea of probability, it's not just some theoretical thing. It has huge implications for how we understand a universe. And it's led to some seriously cool technology.
Oh, that's what I wanted to get to. So this quantum weirdness,
Yeah,
it's not just mind-blowing, it's useful.
absolutely. And that's what we'll dive into next. Get ready to explore the world of quantum computers and quantum cryptography.
Ooh, I'm excited. Stay tuned, everyone.
Welcome back to our deep dive into quantum mechanics. Last time, things got a little weird, right?
Yeah, a little,
Yeah.
but also super fascinating. We went down the rabbit hole of energy quanta, wave-particle duality,
Yeah.
even the uncertainty principle.
All those mind-bending concepts. But now let's see how they're actually being used to make, like, real technology.
Yeah. You mentioned quantum computers last time. I'm really curious about those.
Right. Quantum computers, they're not just faster computers, they're totally different beasts.
Oh, okay, how so?
Well, think about the computers we use every day. They rely on bits.
Bits? Yeah, zeros and
Yeah,
ones.
exactly. But quantum computers, they use qubits. And here's where the quantum weirdness comes in handy. Remember superposition.
Oh, yeah, the whole... a particle can be in multiple states at once.
Right, like that coin spinning in the air.
Right.
Until it lands, it's both heads and tails.
It's like it's choosing all the options at the same time.
Exactly. So a qubit, it can be in a superposition of both 0 and 1, like both at the same time.
Whoa. Okay, so that means, what, it can do multiple calculations at once.
Pretty much. That's why they're so powerful. They can explore tons of possibilities simultaneously. It's like having a million computers working on the same problem.
Okay, that's starting to make sense, but like, how do you even build something that can do that?
It's not easy, that's for sure. Building stable qubits is a huge challenge. Scientists are using all sorts of cool techniques like trapping ions or using superconductors.
It's complicated.
It is. But the basic idea is to create a system where you can control these super delicate quantum states. It's like a whole new level of engineering.
So what are these quantum computers good for? Like, what kind of problems can they solve that our normal computers can't?
One of the biggest areas is simulating stuff, like how molecules behave. Imagine being able to design new drugs or new materials just by simulating how atoms interact at the quantum level.
Wow, so they could speed up scientific discoveries.
Totally. And it's not just that, they're also amazing at optimization problems. Think about like finding the most efficient routes for deliveries in a city.
Ah, so they could, like, solve traffic.
Yeah, potentially. Problems with a zillion possibilities, quantum computers can tackle those way faster.
Okay, so they sound pretty incredible. But are we all going to have quantum computers on our desks soon?
Haha, not quite yet. They're still pretty early in development. They're expensive, they're finicky. It's a whole thing.
So no quantum laptops anytime soon.
Probably not. But they're getting better all the time. Lots of experts think quantum computing is going to totally change tons of industries, just not quite yet.
Okay, makes sense. So we've got quantum computers using superposition to do these super powerful calculations. But what about that other thing you mentioned, quantum cryptography?
Right, quantum cryptography. It basically uses the weirdness of quantum mechanics to make unbreakable codes.
Unbreakable codes. Now that sounds intriguing. How does that even work?
Well, it uses the fact that, remember, observing something in the quantum world, it changes things.
Yeah, that whole mind-blowing thing from the double slit experiment.
Exactly. So imagine you want to send a secret message. You can encode it using the polarization of photons, like whether they're vibrating up and down or side to side.
Okay, I'm following.
Now, because of the uncertainty principle, if someone tries to intercept those photons to measure their polarization, they'll mess it up. It's like a built-in alarm system.
You'd instantly know if someone was eavesdropping. That's so cool.
Yeah, it's pretty neat. And because it's based on like fundamental laws of physics, it's incredibly hard to break.
It's like something out of a spy movie. Is this stuff actually being used, like, in the real world?
It is. It's already being used for super secure stuff like government communications, banking, that kind of thing.
Wow.
And as quantum technology keeps improving, we might see quantum cryptography everywhere, like even protecting our everyday online stuff.
That's amazing. So quantum mechanics, it's not just about weird theories, it's actually shaping the technology we use.
Totally. And this is really just the beginning. As Yurigo Schneppet points out, we've only just started to tap into the potential of quantum technology.
Well, this has been mind-blowing, from the theoretical stuff to all these practical applications. But there's one question I keep coming back to. If observing something can actually change reality at the quantum level, what does that mean for us? Like, are we shaping the universe just by looking at it?
That's a big question. And it's one that's puzzled physicists and philosophers for ages.
It's like, what is the role of consciousness in all of that?
Exactly. Does it actually play a role in, like, collapsing the wave function? It's a huge mystery.
So are we just observers, or are we actively creating reality? It's a lot to think about.
It really is. And it's what makes quantum mechanics so fascinating. It challenges our understanding of, well, everything.
Well said. We've covered a ton in this deep dive, but there's always more to explore.
Always.
You know, it's funny. After diving deep into all this quantum stuff, it's like, I see the world a little differently.
Yeah, I get that. It kind of makes you question everything you thought you knew, right?
It totally does. Like, remember at the beginning how we talked about classical physics just hitting a wall? Couldn't explain things like the ultraviolet catastrophe.
Right. And then Max Planck comes along, like Yurigo Schneppet lays it out in the essay, just throws this wild idea out there. Energy quanta.
Yeah.
Tiny packets of energy, not this smooth flow we always thought it was.
It's such a simple idea when you think about it.
Yeah.
But it totally revolutionized physics. And then Einstein comes in with his photoelectric effect.
Einstein. He really cemented this whole quantum thing, didn't he?
Yeah. Light isn't just a wave anymore. It's a stream of photons. These little packets of energy.
Photons, quanta. It's like the universe is made of these tiny building blocks.
And then that whole wave-particle duality thing. So strange.
It really messes with your intuition, right?
Yeah. Things can be both waves and particles. It's like the universe is playing some kind of cosmic joke on us.
Remember that double slit experiment? You shoot single photons, one at a time, and they still create an interference pattern.
It's like each photon goes through both slits at the same time. It's wild.
And then, the moment you try to peek to measure which slit it went through, the interference pattern disappears.
Like they know they're being watched. It's so strange.
Yeah. And that ties into Heisenberg's uncertainty principle, too. You can't know both the position and the momentum of a particle perfectly.
Yeah.
It's not just our instruments that are limited. It's like a fundamental limit of reality itself. Yurigo Schneppet really emphasizes that point, you know?
But there's always going to be some fuzziness, some uncertainty at that quantum level. Okay,
Yeah.
so all this weirdness, how did physicists even begin to, like, organize their thoughts?
Well, they came up with different approaches. Heisenberg, with his matrix mechanics, he went very abstract, focused on the math, on what we can actually observe.
A more practical approach then.
In a way, yeah.
Yeah.
And then there's Schrödinger. He's all about waves, describing particles as waves using this thing called the wave function.
Right, the wave function. But what does it actually tell us?
Well, that's where Max Born comes in. And his interpretation of the wave function, it was revolutionary, he said. In the quantum world, we can't know everything with absolute certainty. We can only know the probability of finding a particle somewhere.
So it's all about chances then, not certainties.
Yeah. Quantum mechanics, it throws determinism out the window. It says there's randomness, there's chance, baked into the fabric of reality.
Okay, so that's a huge shift in thinking. It's not about knowing for sure, it's about knowing the odds, which actually kind of makes the universe more exciting, don't you think?
Maybe. But the really cool thing is, all this weirdness, it's not just theoretical. It's actually led to some incredible technology.
Yeah, like those quantum computers we talked about earlier.
Exactly. Harnessing superposition, entanglement, to do things our regular computers could only dream of.
And quantum cryptography, making those unbreakable codes. It's amazing how those mind-bending concepts are being used in the real world.
It's like proof that exploring the fundamental mysteries of the universe can lead to really practical, powerful tools.
I keep coming back to that question, though. If observing something can actually change it at the quantum level, what does that mean for us, for our role in the universe?
It's a huge question, right? And it's one that, honestly, we don't have a definitive answer to yet. Some interpretations of quantum mechanics even suggest that consciousness plays a role, like our minds actually influence the outcome of quantum events.
So we're not just passive observers. We're active participants in shaping reality.
Whoa. It's
Wow.
a mind-blowing possibility, isn't it? And it's really at the heart of what makes quantum mechanics so fascinating. It forces us to rethink everything we thought we knew about reality, about ourselves, about the universe.
Well said. Yorgo Ishnepikat really captures that sense of wonder in the essay, that feeling that we're only just scratching the surface of something truly profound.
Absolutely. And who knows what other mysteries and wonders are waiting to be discovered? That's the beauty of science, right? The journey never really ends.
It's true. Quantum mechanics might be strange, might challenge our intuitions, but it's a testament to the power of human curiosity, to our drive to understand the universe, no matter how weird it gets.
Couldn't have said it better myself.
Well, on that note, I think we've reached the end of our quantum journey for today. But keep exploring, keep asking questions, and who knows, maybe you'll be the one to unravel the next big mystery of the quantum world. Until next time, stay curious.